This lecture is part 4 of Chapter 1, The Air We Breathe, in Chemistry and Context, 7th edition. This lecture will cover sources of air pollution, ozone as a pollutant, and sources of air pollution indoors. There are two major sources of air pollution: combustion from coal plants and combustion from vehicles. Let's take a look at coal plants first. So here we have a typical setup for a coal-fired power plant. We've got a conveyor which brings the coal into the plant, sends it into a furnace. The furnace burns the coal. The heat generated from that burning heats water, which converts the water to steam. Steam goes into a turbine, spinning the turbine and thereby generating electricity, which can then be sent out to the community. The problem with coal is that it contains impurities. It's mostly carbon, but there is the impurity of sulfur. The other major source of air pollution is combustion vehicles. The picture on the left here, of course, is exhaust coming out of a car. On the right, we have an electric vehicle, which doesn't emit exhaust, but you have to think, where's that electricity coming from? If that electricity is coming from a coal-fired plant, it's not that much better than a combustion car. However, one advantage is at least if the energy is generated in a single place, we may be able to treat any pollution a little more effectively versus having many different cars on the road that are emitting exhaust. Sulfur containing gases can also be emitted in car exhaust. So if you had to look at some kind of chemical formula, coal, which is mostly carbon but has some sulfur plus oxygen, can form sulfur dioxide. Sulfur dioxide can further react with oxygen to form sulfur trioxide. Here we have the space-filling model of that reaction. 2 SO2 molecules, 1 O2 molecules, forming 2 SO3 molecules. We can see we have 1, 2, 3, 4, 5, 6 red spheres on our reactants representing oxygen atoms, and we have 6 on our product. So this is a balanced equation. So these sulfur dioxide and sulfur trioxide molecules are problematic because what happens is they dissolve in water in the atmosphere, and when they do, they form this H2SO4 molecule, which is known as sulfuric acid. And a bit later on, I'll talk about nitric acid forming as well. And so from cars and from smokestacks, these sulfur-containing and nitrogen-containing molecules then form acid in the atmosphere, and that can then rain down upon the earth. We have been working hard to remove our sulfur from fuels. Diesel fuel typically had much more sulfur than it does now. Also, industrially in coal plants, we're taking a lot of steps to reduce that as well. You might have heard of smokestack scrubbers, basically large filters they could put on a smokestack to help reduce those emissions. NOx is another general term for pollution molecules that contain nitrogen and oxygen. They are what give smog its brownish tinge. And this type of combustion reaction occurs. We've seen this previously. This nitrogen gas plus oxygen gas can form this nitrogen monoxide. Here we have the space-filling model. And really, this is a simplified version of the chemistry that occurs. There are actually a few more steps in the process, but overall, this is what will occur. Once you form that nitrogen monoxide, it can then go on to form nitrogen dioxide and even nitrogen trioxide. So that's why these molecules as a whole are referred to NOx, where that X can be a 1 in the case of nitrogen monoxide or a 2 in the case of nitrogen dioxide. But all of them are problematic when they reach a certain concentration in the atmosphere. So they're respiratory irritants, first of all. They're also, which is even maybe a bigger problem, they're a precursor to ozone formation. And we're not talking about the good ozone formation. We're talking about ozone formation right above the surface of the Earth, not the ozone layer in the stratosphere. Then, of course, they also can make acid rain, as I mentioned earlier. You take some of the NOx, nitrogen monoxide, nitrogen dioxide, dissolve it up in some water up in the clouds above us, and yay, we get nitric acid. Yay, strong acid. And then nitrous acid. Yay, I like acid rain. It tingles. Is this equation balanced? Well, hopefully you've had a second to think about that. What I like to start with is elements that pop out. Now, there are at me. There are a lot of oxygen and hydrogen atoms here. Not many nitrogens, so I'm going to check the nitrogens first. I see 2 nitrogen atoms. 2 nitrogen atoms. So far, that looks good. I see 1, 2 hydrogens, 1, 2 hydrogens. That looks good. 3 plus 2 oxygens. 1, 2, 3, 4 oxygens. It is not balanced. Okay, that was just to practice. We're not going to actually balance this equation right now. Carbon monoxide, we talked about earlier in the chapter. It's also formed in combustion engines. It is monitored by most state DMB testing facilities. And if your car is working very well, the majority of the combustion will be what is called complete combustion. Your gasoline, your mixture of hydrocarbons, hexanes, heptanes, octanes, nonanes will undergo combustion, produce CO2 and water, which is, we don't really want a lot of CO2 in the atmosphere, but this is actually indicative of a complete combustion, which is better than an incomplete combustion, where we have our same reactants, but this time we're forming carbon monoxide and other volatile organic compounds. That's what VOC stands for. Catalytic converters are in the vehicles to help remove some of that uncombusted or the incomplete combustion products. They'll also help convert carbon monoxide to carbon dioxide. So basically it acts as a place where unreacted gasoline compounds will get broken down further or reacted to form carbon dioxide. So these volatile organic compounds, it's just a very general term. It's anything that is carbon-based that evaporates at room temperature. So this is formed alongside carbon monoxide during incomplete combustion, but it's also in a lot of household products. And we'll talk later about a little bit in a moment about ozone formation. But even in your paints, if you are concerned about indoor pollution, you probably want to be looking for VOC free paints. Here's a little paint can, and if we zoom in on it there, it says 0 volatile organic compounds. That means you're not going to have these organic molecules off-gassing from your paint as it dries, which is just going to lower the level of indoor pollutants that can cause irritation or or other problems, potentially cancerous for long-term exposure. Sometimes those volatile organic compounds can also play a role in changing the composition of NOx, so converting more nitrogen monoxide to nitrogen dioxide. It's somewhat of a complicated reaction, but the VOCs interact with hydroxyl radicals that need to be present for this to occur to produce more nitrogen dioxide. And we'll see in a moment how volatile organic compounds also play a role in ozone breakdown and formation. So ozone, here these three spheres represent ozone, the ozone molecule. This reaction, the formation of ozone at the surface of the Earth, again in the troposphere, not where we want it in the stratosphere, is catalyzed by sunlight. So we have NOx, or nitrogen monoxide, dioxide, what have you, plus sunlight will cause the formation of an oxygen radical. That's what the little asterisk means here, which then reacts with oxygen gas to form ozone, O3. And again, we don't want that forming down here close to the surface in the troposphere. Volatile organic compounds can also, with sunlight, form ozone as well. Now, there's a short clip on the formation of ozone, which is a nice little animation here. So, just to summarize, NOx and volatile organic compounds, heat and sunlight form ozone. So this is particularly true in places like Los Angeles that are very sunny, that don't get a lot of airflow in the valleys, and all that sunshine and all those pollutants. Perfect combination for smoggy, ozone-filled air, unfortunately. So ozone is a lung irritant. It can make your eyes burn. It also can react with volatile organic compounds to make other photochemical smog. It can cause rubber to crack, can kill plants. It's just not something we want in the troposphere. Ozone in the stratosphere, good. Ozone in the troposphere, near the surface of the Earth, bad. Now this relates somewhat to a term or an expression called the tragedy of the commons. It's when there is a shared resource that no one is actually responsible for. Then if there are no consequences to overuse or abuse, it unfortunately becomes overused and abused by everyone. So if there's a shared resource like the ozone layer, well, perhaps overfishing is a better example. You know, if someone overfishes up here, they're not as aware of how that may impact other areas. And so as a community, global community, we really need to be aware of any shared resource and how, even if we may not be responsible for it, how it does impact us as a global community. Here are some pictures of photochemical smog. Again, it's cities that don't have good airflow where those NOx and VOCs can build up and then with the sunlight form our ozone and other smog compounds. And we've made some improvement with the amounts of air pollutants, 1970 versus 1977. This bar graph here showing the metric tons per year emitted, And you could see carbon monoxide, this is in the United States, has dropped from 120 metric tons to about 80. And we're making inroads on sulfur dioxide and volatile organic compounds as well. This is comparing to 1997, so hopefully we've made even more progress. Unfortunately, it looks like the nitrogen oxides have increased a little bit. Now we've talked about outdoor air pollution, but indoor air pollution can actually be more dangerous. If you don't have a lot of airflow, particularly if you have a newer house that has very good insulation and the windows seal very well, you can build up concentrations of some of these chemicals to a much larger degree than you might see outdoors. So we also combust material inside. Wood stoves, any kind of heaters that use gas or perhaps kerosene. Those molecules, then NOx and the carbon monoxide and the volatile organics can build up. Then, of course, cigarettes. Hopefully you don't smoke indoors. Even if everybody's a smoker in the house, you should not be smoking indoors if possible. Burning candles do also emit these compounds. Candles are a petroleum product. Wax is obtained from crude oil. As I mentioned earlier, paint, if it's not volatile organic chemical or compound free, will be releasing those VOCs, paint. Fingernail polish, glues, dry cleaning, the organic compounds used in dry cleaning, those will off gas while sitting in your home. The garage can be a place of high concentrations of volatile organic chemicals if you have a lot of keep your solvents and pesticides and other compounds, as well as when the car is started in the morning. If you close the door right away, then those chemicals will stay in there. And then radon is the third big one. Radon is a gas that's naturally radioactive and naturally bubbles up through the Earth's crust. You can't actually see it bubbling. And here, this map here, well, first let's look to the left. We see radon on the periodic table. It's a noble gas. So noble gases are supposed to be unreactive. And it is chemically, but as far as from a nuclear chemistry perspective, it's the atom itself is unstable. The radon isn't reacting with anything per se. It's actually splitting apart into smaller atoms. And when that occurs, very high-powered or radioactive energy is given off. And we'll talk more about that in Chapter 7. This map shows the radon distribution in the US. So if you're in one of these blue or green regions, you need to make sure you monitor your radon, particularly if you have a basement. We live up here in Portland, and only more recently has it come to the attention that, particularly in North Portland and Northeast Portland, there are some actually high levels of radon deposits or high levels of radon found in homes. So if you are in Portland, in the northeast Portland, you should have perhaps a radon detector in your basement or have it checked every so often. The detectors and the home kits to check the radon are fairly straightforward. Unfortunately, if you do find a high concentration of radon, you'll have to install something to mitigate the radon. It basically acts as it absorbs the radon. It'll filter the air, and those cost, I think, around $1,500. So I hope you don't find it. But if you do have radon, high levels of radon in the home, it will cause and increase your chances of all sorts of cancers. So keep that in mind when you're going to paint a room, burn some incense. How well is your kitchen ventilated? All of these are actually can be, again, more dangerous than outdoor air pollutants due to the speed in which and they can build up to a more significant concentration. Now let's try to conceptualize how many molecules are actually in a breath. When you take in a lungful of air, you're taking in about 2 times 10 to the 22nd molecules. This picture here is just, this fellow is testing this young woman's ability to take in a breath, measuring lung capacity. But for the average person, this many molecules zoom into our lungs when we take a breath of air, which is a lot. So think about for a minute, see if you can calculate how many of those molecules are nitrogen gas. Let's assume you're breathing really clean air. Based on what we learned previously in Chapter 1, how many of those molecules are nitrogen gas? Once you've determined that, think about for a moment what determines how many numbers we write down after doing a calculation. Do we write down every single number our calculator spits out? Ponder these two questions for a moment. So for the first question, how many of those molecules are nitrogen gas? Well, we know that the atmosphere is roughly 78% nitrogen gas. If that's the case, we should be able to multiply this number by 0.78. I added an extra digit here. That should have been there as well. But 2.0 times 10 to the 22nd molecules times 0.78. If we take the answer that comes from our calculator, it ends up being 1.56 times 10 to the 22nd. Molecules are nitrogen out of 2 times 10 to the 22nd. The majority are nitrogen. But now, do we write down every single number? What if for some reason it gave me an even longer value, like 1.5629? Would it make sense to write those numbers, all of those numbers down? Well, the rule of thumb is that you want to stick with the fewest numbers given in the original question. That's a very general rule of thumb. But if they only give you 2 digits here in the data, or you only know the percentage to 2 digits, when you're doing multiplication and division, you pretty much want to then keep it to 2 digits, just roughly. We're not going to go into any more detail than that, but if you're curious, you can go and on YouTube enter something called significant figures, and you'll get more information. This ends the last part of Chapter 1. Now that we've completed Chapter 1, you should be ready to complete the homework for Chapter 1.